Well, a warm welcome to anyone joining. Thank you for being here. Go ahead and get yourself ready with a notebook. Grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today, we have some Calc AB review for my Calc BC students, also my Calculus 2 students in the audience. Today we're going to take a look back at implicit differentiation as well as logarithmic differentiation, which is a technique that goes hand in hand with implicit differentiation. There are 3 problems here up on the board. For the first one, parts A and B are clear. For the second and third problem, I want you to differentiate. Basically, I want you to find, I should be a little bit more specific. I want you to find dy dx. Okay. I would say give yourself about 10 minutes, 12 minutes total. If I had to parse it out, I would say something like maybe 6 minutes on this one, 3 minutes on each of these. I think that's reasonable. But in any event, accuracy is the most important feature. So whatever pace you can do it accurately, just make that as fast as possible. Okay? Then when you're ready to see how it was done here, you can unpause the video and check us out. Alright, so first let's just take a little recap about implicit differentiation, how it works. So if we have some expression u, which is a function of y, g of y, so it can be something happening to the y, like y squared, y cubed, that kind of thing, sine of y, that kind of thing. Then the derivative of u, which we call du dx, can really be thought of as just the derivative of u with respect to y. And for this part, we just take a normal derivative. We just treat y like it's the variable, and we take a derivative with the power rule or whatever it is you have to do. We treat it as a normal derivative, and then we have to multiply by dy dx. We slap a dy dx on it. And what you'll notice is that because of how we multiply fractions, this in fact does become du dx. Now we don't want to cancel it like that, but this just shows that they are equal, that this equation is valid. So what are we effectively going to do? We're going to take this derivative as normal, and then we're just going to write dy dx on it. This is actually what we're after, because we're trying to find the change in y with respect to x, which is, the delta y over the delta x, or the rise over the run, as you guys might know this from years in the past of studying slopes. All right, so that's just a reminder of how to execute some of these problems. Let's look at a quick example before we get into those 3. So if I have something like 3x squared minus 2y squared equals 7x. When I take a derivative of both sides, d dx, this one works out nicely. This is very easy. It's just 6x because I did it d dx. But for this here, I have to treat it like a function of y. And what do I do with that function of y? I take its derivative as normal with respect to y. So this is 4y, right? Power rule, simple. But then I have to slap a dy dx on it. And this is going to be equals to 7. So you would do some rearranging. I don't know, what would this be? You would get 7 minus, I guess it would be 6x minus 7 over 4y. That would be your dy dx. Okay, so that's the quick review. Let's actually get into some of these problems now. First problem gives us an equation. It's not too important if you know what this looks like. I'll be honest, I don't know what this looks like right off the top of my head. I have an idea of what shape it is, but I don't know where it's placed exactly. And it's not that important to know that. But if you're interested, you can look up the equation on Desmos. Feel free to type that in. All right, part A says find the equation of the normal. Whenever I see equation of the line, whether it's a tangent or a normal line, I always want to write the point-slope equation down. And what's nice is that they've given us the x value and the y value, so we don't have too much work with that. That means that there's going to be more work involved in finding the actual slope. So remember that the normal is the perpendicular slope. It's not the tangent slope. That's important to keep track of. Write it down so you don't forget it later. Now let's just find dy dx. Dy dx will be the tangent slope, and from there we can get the perpendicular slope. If we take the derivative of both sides of the equation, the right side just stays 0. The left side, we have a product here, 2x times y. Remember that the derivative of a product, we just take a derivative of the first one and multiply it by the second one. So that's going to be 2 times y, plus, we're going to leave the first one alone and take a derivative of the second one. And be careful here, because we're taking a derivative of some g of y. What's the derivative of y? Well, it's just 1, but then we have to multiply by dy dx. Okay? And then the last term, negative 6y, we just do the power rule, but you have to attach this dy dx. Okay, great. So let's move everything with dy dx onto one side only. I guess I can leave it on this side, and we'll take it out. So let's take out the dy dx from the left side, and we should have 2x minus 6y. Then on the other side, we will have moved negative 2x and negative 2y. These two things got subtracted over. And so dy dx, which is the parallel or tangent slope to the graph, is negative 2x minus 2y over 2x minus 6y. And we can go ahead and now plug in the point 1, 1. Negative 4 over negative 4. Look at that. We have a slope of 1, but remember, this is the tangent slope. We want the perpendicular slope is going to be the negative reciprocal of our slope 1, which is really easy, just happens to be negative 1. So the equation of the equation of normal line would be as follows. And you can leave it like this, or if you really want to, you can go ahead and write it in this format, which will be kind of useful for part B. So let's look at part B. Part B says, at what other points does the normal line in part A, intersect the graph? So we want to know, when does this line intersect the graph of the equation? Well, if they intersect, this means they have the x and y the same, which means that I can plug in the equation for the y. I can plug this y value, or this y equation, into the original equation. Here we go. X squared plus 2x times y, but instead of this, I put negative x plus 2, minus 3 times negative x plus 2 squared equals 0. This will result in a quadratic equation, and we can solve that quadratic equation easily. What does this quadratic equation represent? It represents when this expression for y is intersecting with the equation. So when we find x or y values, they will be points where this line does intersect the equation. Okay, let's work this out. We're going to have x squared minus 2x squared plus 4x minus 3x squared. I'm going to do this all at once, and you have to sort of be quick about these kinds of things. This is algebra stuff now, right? Would be minus 4x, but now is plus 12x. And then would be plus 4, but is now minus 12. And this all equals 0. So let's condense some of these things together. We're going to get negative 4x squared plus 16x minus 12 equals 0, which we can easily factor a negative 4 out of. And here we have two factors, x minus 1 and x minus 3. We already know about the x minus 1 factor, because we know that x equals 1 is a point on the line and a point on the equation. That's how we got that normal line from part A. by using the point 1, 1. But this other one is new. X equals 3. And if x equals 3, then we can use the equation y equals negative x plus 2 to figure out that y equals negative 1. So the other point which the normal line intersects the equation is 3, negative 1. Okay, so that is a little bit of a glance at the kind of word problem they might ask you using implicit differentiation, like a part A and a part B. The other parts would surely be tougher, like finding the second derivative or something like this. Let's take a look at these two problems, which are effectively the same structure. These are neither power functions, which has x as a base and a constant as a power, but it's also not exponential, which has a constant as a base and a variable in the power. This is kind of a hybrid. It has a variable in the base and it has a variable in the power. So we have to use the technique called logarithmic differentiation along with the implicit ideas that we looked at earlier. So how does this work? Well, since it's neither fitting type, we're going to first take a log of both sides, because if these two things are equal, then their logarithm values must be equal. But now that we've transformed the right side of the equation into a logarithm, we can use the power property. You guys should know the power property to bring this in front. And now we have radical x times ln of x. And on the left side, we have ln of y. So we've just created ourselves a g of y. Remember what I was talking about earlier. When we have a function that is some g of y, we have to take its derivative as if y was the variable first. So just treat it like y is the variable, and then we slap a dy dx on it. Okay? So let's take a look at our problem. Go back to here. We take a derivative of both sides. So you can write that if you want to be technically correct. And so we're going to take a derivative as if y is just an x, like we're going to treat it like we normally do. 1 over y. But then we have to slap a dy dx on it. And this is really what we're after, is this dy dx. That's the goal of the problem, is to find dy dx. Now on the right side, we have ourselves a product. Time to use the product rule. So what is the product rule? The product rule says take a derivative of the first thing and multiply it to the second thing. This is going to be 1/2 x to the negative 1/2. You guys should totally know this. You're in Calc 2 by now. And we leave ln of x the same. Plus, now we're going to leave the square root of x the same and multiply it by the derivative of ln. You could put it as square root of x or x to the 1/2. Doesn't really matter. And then we're going to multiply by the derivative of ln of x, which is just 1 over x. Okay, well, to clean this up a little bit, I do want to point out that this can be simplified. This is essentially the square root of x over x, which is x to the 1/2 over x to the 1, which is x to the negative 1/2, like the denominator has a higher power. So really, I could also factor this out. I think I will. So we're going to have 1 over y, I'm going to show my work carefully, 1 over y dy dx equals 1 over square root of x times 1/2 ln of x plus 1. And then we multiply both sides by y because we need to get the dy dx by itself. So you're going to see this come up anytime you do logarithmic differentiation, because you're going to create a logarithm and its derivative is always going to be the same, 1 over. So get used to multiplying both sides by y so that we can cancel this and get the dy dx by itself. So this is going to be y times x to the negative 1/2 ln x plus 1. And then if we want to put the y back, what was the y expression? The y was x to the square root of x. So we have x to the square root of x times x to the negative 1/2 times 1/2 ln of x plus 1. Now at this point, you don't even have to write it as that necessarily. Didn't have to simplify it the same way, but I'm just showing you things that can be done. So I would probably write it as x square root of x minus 1/2 like put them together because they're being multiplied, so you can combine their powers. Then we have 1/2 ln of x plus 1. That is our derivative. So it took me more than 3 minutes, but it's because I really went out of my way to simplify things, probably extra than you really needed to, but it looks clean now, doesn't it? All right, let's move on to the last problem here. Sine 2x, which is a non-constant base, it's a variable base, it's changing. Not only is the x changing inside, but the sine of 2x is changing. And we have a variable in the power as well. So you probably know the drill. We're going to take a logarithm, natural logarithm, of both sides. And that's going to allow us to use the nice power property of logarithms. Notice that the power has to be on this thing inside of the logarithm. It's not on the overall logarithm. Like if I had a 3 here, I cannot just move the 3 to the front. It has to be on the actual argument of the logarithm. Okay, little digression there. Let's use the power property. Get the 4x in front, and now we have ln of y equals 4x times ln of sine of 2x. So we have some chain rule, that's for sure, and a product rule. Let's get differentiating. If we differentiate the left side, of course, no surprise, we get 1 over y and slap a dy dx on it. Now on the right side, because we have a product, let's carefully use the product rule. Color coding is your friend here, guys. Honestly, it is. 4, that's the derivative of 4x. And then we just leave this thing alone, sine of 2x. Plus, now we're going to leave the first thing alone and multiply it by the derivative of the second thing, which is probably going to be kind of lengthy because we have a couple chain rules in there. 4x stays the same. Now we have 1 over sine of 2x. Then we have to multiply by the derivative of sine of 2x, which is cosine of 2x. Then we have to multiply by the derivative of 2x, which is 2. Okay, so even though that looks a little messy, we can clean some of this up. This is cosine, and this is 1 over sine. That's going to turn into cotangent of 2x. And then we can multiply 4x times 2. That gives us 8x. This is looking pretty clean so far. And this is going to be a plus in between them. Now that's equals to 1 over y dy dx. So if we multiply this whole thing by y, we get our dy dx. And yes, you do have to put that back. You have to put in sine of 2x to the 4x. Times this whole thing. 4 ln of sine of 2x plus 8x cotan 2x. It's a bit hefty, but that is the final answer. I almost want to double check it. It feels like something's off, but I don't think it is. So what's the trick here? We take a logarithm. That way we can take advantage of the power property. And this is what allows us to take a derivative much smoother. Otherwise we'd be stuck. Okay. So if you're in Calc 2 and Calc BC, you need to get up to speed with implicit differentiation. We're going to take a look at this topic again in the applied form of related rates. So stay tuned for that one. I think that's enough blab out of me. I'll see you guys next time.